Okay, I want you to use your imagination for a second. Picture the most basic thing you do in the kitchen. You take a pot of cold water, you put it on the stove, you turn that dial all the way up to high, and you just stand there, watching the blue flames lick the bottom of the pot. Now, if I were to ask you, what is actually happening to that water? You'd probably say,
Well, it's getting hotter.
naturally, you're adding energy, so the temperature goes up.
Of course.
Right.
Yeah.
And if I push you a little bit, if I ask, okay, but what is temperature?
Yeah.
And most of us, I think, we'd fall back on our high school physics and say, it's speed.
Right. It's the jiggling.
Exactly. We picture these little water molecules like tiny billiard balls, and as they get hot, they just start bouncing off each other faster and faster.
And that is the classic textbook definition. Temperature is the average kinetic energy of the particles. It's written in bold in, almost every science classroom in the world?
But here's the problem. If you keep watching that pot, the water, it eventually boils. It's churning, it's bubbling like crazy.
Yeah.
And you are still pumping a massive amount of heat into it.
Yeah.
From that burner. But if you stick a really precise thermometer in there, the number stops moving.
It just stalls.
It hits 100 degrees Celsius, and it flatlines. The energy is still pouring in, but the temperature isn't going up.
And if temperature is just speed and you're adding energy, then why does the speed stop increasing just because the water's turning to steam?
Exactly. Why does the line go flat? And that is just one of the cracks in the foundation we're exploring today. We're doing a deep dive into a really fascinating paper by Jerry Z. Liu. It's titled, Can Temperature Represent Average Kinetic Energy?
And to sort of spoil the ending, his answer is a very firm no.
It really is.
It's a fascinating piece of work because it really challenges something we all just take for granted. Liu argues that for centuries we've been mixing up two different things. We think temperature is motion,
Right?
but he makes a compelling case that temperature is actually a measure of radiative and potential energy. The motion, that's just the exhaust pipe of the whole process.
It's a complete flip of the script. We're going to get into why your gas mileage predictions are, well, theoretically wrong, why water actually shrinks when you heat it, which is incredibly weird, and why your infrared thermometer even works at all.
And to really get why we need a new theory, we have to start with why the old one fails. And to do that, we have to talk about the ideal gas law.
Oh, the dreaded PV equals nRT. I think I still have stress dreams about that equation from my junior year.
You and me both. But the core assumption of that law and the kinetic theory that comes from it is very specific. It says the kinetic energy of a gas, literally the energy of its movement, is directly proportional to its temperature.
So a simple linear relationship, double the temperature, you double the kinetic energy, the particles fly around twice as fast. It's neat, it's tidy.
In theory, and here's the thing, if you test this on something like helium, it works perfectly.
Oh, really?
Perfectly. Helium is a noble gas, just a single atom floating around. The kinetic theory predicts its behavior with 99% accuracy.
Which is probably why the theory has stuck around for 150 years.
Yeah.
If it works for helium, we just assume it works for everything. We pat ourselves on the back and say, job well done, physics.
But the universe is not made entirely of helium. And this is where Liu's paper really, really shines. He highlights this massive discrepancy when you start looking at more complex molecules. He brings up the data on specific heat.
Okay, specific heat. It's a term we hear a lot, but maybe let's just define it to be safe. It's basically the thermal inertia of a substance, isn't it? How much energy you have to jam into something to get its temperature to budge by 1 degree.
Correct. It's a measure of its energy capacity. So
Yeah.
now let's look at octane. That's the stuff in your car engine. It's a big, complex chain. 8 carbon atoms, 18 hydrogen atoms.
Okay.
If you use the classic kinetic theory, that old billiard ball theory, to predict how much energy it takes to heat up octane, the math says you shouldn't need that much.
Because if all the energy is just going into speed, you just push the molecule and it goes, shouldn't be that hard to do.
But when you actually run the experiment, the prediction fails. I mean, badly. The kinetic theory only accounts for about 7% of the energy you actually have to put in.
Wait, 7%?
Just 7.
So you're telling me there's a 93% error rate?
93% of the energy is just missing. You are pumping heat into this octane, but it is not showing up as speed. The kinetic model has no way to account for where that energy went.
That's like filling up your gas tank and having 93% of the fuel just vanish before it even hits the engine.
Exactly.
That is not a rounding error. That's a catastrophe for the theory. So where is all that energy hiding?
That's the central mystery Liu tackles, and he found a pattern. If you look at a chart of different substances, helium, hydrogen, octane, the error rate correlates almost perfectly with the number of bonds in the molecule.
Okay, let's trace that out. Helium has 0 bonds, and the theory works.
Right.
Hydrogen gas is 2 atoms bonded together. The theory starts to drift a bit. Octane has 25 bonds, and the theory just completely collapses.
Precisely. This strongly suggests that the energy isn't going into moving the whole molecule across the room. It's going inside the molecule. It's being stored in the bonds themselves.
The paper uses an analogy here that I really liked. It says, we need to stop thinking of atoms as these hard billiard balls and start thinking of molecules as systems of springs.
It's such a crucial shift in visualization.
Yeah.
Imagine a complex molecule is like a mattress with, say, 25 springs inside it. When you hit it with energy, with heat, you aren't just knocking a whole mattress across the floor.
You're compressing and stretching all those internal springs.
Yes. So the energy is being captured as potential energy within the structure rather than as kinetic energy of the whole object moving.
And that explains the missing 93% in the octane. That huge amount of heat is being used to just stretch those carbon-hydrogen bonds. The molecule itself might not be flying around much faster, but internally, it's under tremendous tension.
And this explains something else that always seemed kind of weird to me about liquids versus gases. Well, logic would tell you that a gas, flying around like crazy, should hold more motion energy than a liquid, which is just sort of sloshing around.
That's the intuition. If temperature is speed, gas wins, hands down.
But let's look at the data in the paper. Table 2 compares the specific heat of substances in their liquid versus their gas form. Take water. Liquid water has a specific heat nearly 3 times higher than steam.
So it takes 3 times as much energy to heat a cup of water by 1 degree than it does to heat the same amount of steam.
If temperature were just speed, this would be impossible. Steam molecules are zooming, water molecules are all stuck together. But if you see it through the spring model, it makes perfect sense.
Because liquid water is a network. It's all held together by hydrogen bonds. It's like one giant interconnected web of springs.
Exactly. It's like a ball pit where every single ball is connected to its neighbors by little elastic bands. You can dump a huge amount of energy into that web, and the springs just stretch and store it.
Whereas steam has already broken those bonds, the springs are snapped.
Right. There's nowhere left to store the energy, so any new energy just immediately creates speed.
It seems like chemists have kind of known this for a long time, haven't they? They talk about bond enthalpy, energy storage. Why is physics lagging behind on this?
It feels like a silo problem. Chemists are looking at the bonds and the reactions. Physicists, especially when teaching thermodynamics, tend to look at the bulk movement. We're still teaching the ideal gas law because it's, mathematically elegant, even if it's physically incomplete for complex matter.
Okay, so if we accept that temperature isn't mostly about motion, but about this internal stretch, then how do we actually measure it? Because when I use an infrared thermometer on my pizza stone, I'm not measuring stretch. I'm measuring light.
And that brings us to the second pillar of Liu's argument. Temperature is fundamentally a measure of radiation.
This is the part that connects what we feel to what is actually happening.
Yeah.
We all know hot things glow. You heat up a piece of iron, it turns red, then orange, then white.
That's the Stefan Boltzmann law. It says that the power of the radiation coming off an object is proportional to its temperature raised to the 4th power, T to the 4.
That's an incredibly strong relationship. You just tweak the temperature up a little, and the radiation output explodes.
It does, and this glow happens all across the spectrum. Your pizza stone is glowing in infrared, which you can't see, but the sun is glowing in visible light. Green-blue, actually, according to the paper, which our eyes just mix together to see as white.
Okay, but here is the critical question. What causes that radiation? Does an atom bumping into another atom create light?
No, that's not how it works.
I remember this from chemistry. Light comes from electrons jumping around.
Specifically from quantum transitions. Think about an atom like a tiny solar system. You have the nucleus, and then you have electrons in these shells, or orbitals. When an electron in a low energy state absorbs some energy, it jumps up to a higher, further out orbital. That is an increase in potential energy.
It's like lifting a rock to the top of a tower. You've stored energy in it just by moving it up against gravity's pull.
Precisely. And when that electron inevitably falls back down to that lower shelf, it releases that stored energy as a photon. It emits radiation, light.
So let's just follow the logic chain here. Temperature is measured by radiation.
Right.
Radiation is caused by electrons jumping between orbitals.
Yep.
And those electron jumps are changes in potential energy.
Therefore, temperature is a measure of potential energy.
That's the transitive property right there.
And it completely sidelines kinetic energy. The jiggling isn't the cause of the temperature. The state of the electrons is the cause. The hotter something is, the more its electrons are being pushed into those high, unstable, high potential orbitals.
Okay, I am with you on the potential energy and the radiation. That explains the thermometer. But I can't shake the feeling that motion is still involved. If I stick my hand in that boiling water, the pain I feel is from molecules slamming into my skin. Right?
Yeah.
Things do move faster when they get hot. We can't just deny that.
We don't deny it. But Liu argues that the motion is a side effect, and he introduces a mechanism to explain how that potential energy turns into kinetic energy. He calls it transimpact.
Transimpact. Sounds like something out of a sci-fi drive system. Engage the transimpact thrusters. How does it actually work?
It's surprisingly mechanical, so imagine a single atom. It absorbs some thermal radiation. An electron jumps up to a higher outer shell.
Okay, so the atom is now excited. It has high potential energy.
But think about the geometry of that. When an electron moves to a wider orbit, the effective size of the atom itself increases. The atom physically gets bigger.
Like a balloon inflating.
But instantly. We're talking nanoseconds. It's an explosive expansion. The paper compares it to popcorn popping. One moment the atom is size X, the next it's size X plus a bit.
And since atoms in a liquid or a gas are packed pretty close together,
that expansion has nowhere to go but into its neighbors. It shoves them hard. And that forceful shove, that is kinetic energy.
Ah, I see. So the sequence is the electron jumps, that's the temperature rising, then the atom expands, then that expansion physically hits its neighbor, and then the neighbor flies away.
Exactly. The motion is the result of the pop. The kinetic energy is the shock wave from the temperature change, not the temperature itself.
That is a really cool mental image. It's like being in a super crowded room where everyone suddenly opens an umbrella at the exact same time. People are going to get shoved to the edges violently.
That's a fantastic analogy. And this mechanism, it explains the famous Crookes radiometer. You've seen those light mills, the little glass bulbs with vanes that spin in the sun?
Yeah, the classic physics toy. One side of the vane is black, the other's white. I always heard it was the pressure of light pushing them.
That was the old debate for decades. But the calculations showed light pressure just isn't strong enough to spin them that fast. Liu argues it's transimpact. The black side absorbs radiation, the atoms on that surface get excited, they expand explosively, pop, 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 and that mechanical kick against the few air molecules left in the bulb is what pushes the vane.
So it's literally an atomic combustion engine. It's capturing heat, expanding, and creating thrust.
In a way, yeah. And this mechanism also works in reverse. He calls that impact trans.
Impact trans. So I assume this is how friction works.
Correct. Just rub your hands together right now. You are mechanically forcing atoms to collide with each other. That kinetic impact squeezes the atoms. It forces the electrons into those uncomfortable higher orbitals.
So you're physically pumping potential energy into them just by smashing them together.
And once they're up there, they're unstable. They want to drop back down, so they do, releasing a photon. And you feel that as radiant heat, warmth.
So the cycle is complete. Kinetic becomes potential. Potential becomes radiation. But the actual state of being hot, what we call temperature, is fundamentally the potential and radiative part of that cycle.
You've got it. And once you start to view the world through this lens, those thermodynamic mysteries we mentioned at the start, they just vanish.
Okay, let's go back to the boiling water. The phase transition paradox. Why does the temperature flatline at 100 degrees? This has always bothered me.
Well, in the classical view, we sort of hand wave it and say, oh, the energy is being used to break bonds. But if you break a bond, the particle should fly free, it should speed up, the temperature should rise.
But it doesn't. It just sits there.
In this new dynamic energy model, just remember that temperature is the stretch of the spring. It's the potential energy.
Okay.
Imagine you're stretching a rubber band. You pull it, the tension rises, the temperature rises. But eventually, you stretch it to its absolute limit. You cannot stretch it 1 millimeter further without it snapping.
The tension hits the ceiling.
Exactly. The potential energy plateaus because the bond is maxed out. And since temperature measures potential energy, the temperature plateaus too.
Even though I'm still pouring energy in.
Yes, that extra energy can no longer go into stretch, so where does it go? It goes entirely into the snap, the transimpact that finally breaks the bond and sends that water molecule flying off as steam.
So the kinetic energy does skyrocket at that moment. The steam flies away. But since the thermometer isn't measuring speed, it doesn't care.
Precisely. It explains the decoupling of speed and temperature perfectly. The thermometer measures the tension in the rubber band, not how fast the pieces fly when it snaps.
There's one more mystery I want to touch on because it's so counterintuitive. Thermal expansion. Generally, things get bigger when they get hot. The textbook says it's because they vibrate more and need more elbow room.
Which sounds plausible, right? Until you looked at the water anomaly.
This is the weird fact that water actually shrinks when you heat it from freezing up to about 4 degrees Celsius.
Right. If heat were just vibration, water should expand immediately as soon as you warm it up. Vibration needs more space. But it contracts. The vibration theory can't explain that.
So how does the bond theory explain it?
It comes down to structure. Ice isn't just a random pile of molecules, it's a crystal. The hydrogen bonds form this rigid scaffold holding the molecules in a wide hexagonal pattern. There's actually a lot of empty room inside an ice crystal.
Like a house of cards, maybe.
That's a good visual. Now, as you start to heat it, you trigger those transimpacts, the electrons jump, the atoms pop, and this violence disrupts that delicate scaffold.
And the house of cards collapses.
It collapses, the structure fails, and the molecules fall down into all those empty spaces. So even though the individual atoms are getting more energized, the bulk volume of the water decreases. It gets denser.
Until all the scaffold is gone at around 4 degrees.
And then the normal electron expansion mechanism takes over, and water starts expanding like everything else. The vibration theory fails to predict this, but the bond and potential theory predicts it naturally.
It's really striking. When you stop looking at the bumping and you start looking at the bonds, the behavior of matter actually starts to make sense.
It really changes your perspective on the universe. You stop seeing heat as just activity and you start seeing it as a state. It's the stress level of the electrons in a system.
So to wrap this up, let's talk about the big picture. The paper proposes a new formula to replace our old kinetic one.
Yes. Liu proposes the dynamic energy model. It's a triad. The total thermal energy equals radiative energy plus potential energy plus kinetic energy. So E equals R plus U plus K.
3 faces of the same coin. Or maybe 3 faces of the same die, I guess.
And they are constantly converting into one another. But we have to stop pretending that K kinetic energy is the boss. In many cases, especially with complex matter like our bodies or water or the atmosphere, U potential and R radiative are the dominant players.
It's a really compelling argument. It makes me wonder what else we're measuring with the wrong ruler just because the math is easier.
It's a common trap in science.
Yeah.
We stick with the spherical cow in a vacuum because the math is so clean. But the real world is messy. It's bonded and complex.
Before we sign off, I want to leave you with a thought that really struck me reading this. We always talk about absolute zero, 0 Kelvin. And we usually think of that as the point where all motion stops. Everything just stands perfectly still.
But if we apply this new lens...
If temperature is radiation and potential energy, then absolute zero isn't about stillness. It's about darkness.
That's profound. It would be a state where every electron is in its absolute lowest possible orbital. There's no potential energy left to give. No radiation is possible. So even if a particle were drifting through space, if it has no internal glow, it's at absolute zero.
And to go even deeper, if kinetic energy is just the exhaust, just the pop from an electron jump, is all the motion in the entire universe just a side effect? Are we all just moving around because the universe is constantly trying to balance its potential energy?
That really turns physics on its head. It suggests that potential is the driver, and kinetic is just the result. The universe moves to try to get comfortable.
Something to chew on next time you boil a pot of water. It's not just bubbling. It's a network of springs screaming under tension.
I will never look at tea time the same way again.
Thanks for taking this deep dive with us.
Always a pleasure.
Catch you on the next one.